Okay, now I'm not sure we can even see the whole meter stick in the picture, but it's a meter stick. Here's the 50 centimeter mark. And the thing balances pretty well, close to the 50 centimeter, okay? Not perfect, it's closer to the 49 and a half, 49 centimeter, but apparently the meter stick is heavier on one side than the other. Okay, to use terms. Now I'm gonna put the meter stick like this so you can see the whole thing. I'm gonna say, if I try to balance it around this end, what happens? Well, rather quickly goes down. If I want to prevent it from going down, just with my thumb and forefinger, it takes a little effort. Okay, now if I hold it with my wrist, it doesn't much. Okay, so there it is, and I can wiggle it. The reason it balances here in the middle, you can see the middle, it's because the torque that tends to rotate this end around here, torque that tends to rotate this end around the center, is equal and opposite to the torque that tends to rotate this end around the center. Just to understand torque a little bit, we took this, kind of like 50 grams or 60 or 70. So it's a, type, it's a demonstration capacitor. It's not worth much except for demonstration. It's great for that. Okay, we put this out at the end. We held the meter stick at the other end and we wiggled the thing. Okay. Then we wiggle it without the thing. It's half a dozen times harder to wiggle if this thing's out here. Okay. If this thing's out at the end. Now we wiggle it with this thing close to where my hand is, and we take it off. Doesn't make much difference. This thing doesn't exert much torque here. It exerts a whole lot of torque if it's out here. Way more than just a meter stick by itself. Okay. Now, if I put this thing here, okay, well, I'm going to just put it 10 centimeters from the balancing points. Okay, now if I release it, it's going to rotate this way because you got more torque on this side than you got on this side. Again, the torque of the meter stick itself is the same on both sides if I'm at the balance point. So the question now is, where would I have to balance this? If I move my finger over this way, far enough, okay, somewhere right around here, okay, about halfway between the 50 centimeter mark, and this is a 60 centimeter mark here. So about the 55 centimeter mark, I get a balance. That's because the torque on this side, just due to the meter stick from here to the end, balances the torque of the meter stick from here to the end, the shorter part of the meter stick, plus the torque exerted by this thing. Okay. Let's just test that. Seems like if I moved it halfway, that works. If I move it halfway now, is it going to work? Not quite. I don't move it quite halfway. And it's just because that we could write it out, but I'm not going to do that. Okay. So I move it. This is at 50. This is at 70 centimeters. And it's at about 59 centimeters here. It's balanced. Okay. Now you can do all kinds of stuff with that. The problem is that the center of mass for any mass distribution, let's say we got something that's shaped like this, okay? The center of mass point where the torque exerted by this part is equal and opposite to the torque exerted by this part. Okay. Now, it turns out that if I've got, well, this stands for X left. The torque equals F left equals well, let's say that this line that depicts the center of mass is at X center of mass, okay? The torque about X equals X sub L is equal to the weight times this distance, okay? Now you can see that the vector diagram, it's just like you got the weight here. Times, I'm going to call this the moment arm. Something that you would have encountered in middle school general science if our educational goals were to maintain a technological society, which they apparently aren't. Okay, somehow we're still doing it. We'll see how current policies impact that. Could be good, could be bad, reserving judgment. Some things stirred me a little bit, some things look pretty good. But okay, so you got moment arm times weight. Now then you can relate that to the fact that if you just ignore the little bit of torque you need to support the meter stick, you put this thing out here, you got a certain amount of torque that you need, right? Put it further out and you drop it on the floor, but you need more torque. Okay? Now, fortunately, it wasn't charged. You would have blown us all up. Okay. That should relate, yeah, in your intuition to this. Okay? If you ever get through medical science, school science, and haven't taken a crowbar and done something with it, so you understand something about torque again. Well, you can't use crowbars in a middle school. You'd end up with dead people. Seriously, that would be dangerous, but you can use little wood levers and stuff and learn a lot of stuff. It only takes a day, if that. But I don't know what, anybody ever do anything like that in middle school? It doesn't take much. A little bit gets the ball rolling, and then you start to develop some real intuition. So that when you get to where you need to understand this, you got a better handle. Okay, well, one way or another. And if you've had some physics, only 60% of the high schools in this country offer physics. A lot of people should be in jail for that. Okay. I mean, it's just nuts. But it's funny. And I understand the reason for it. It's just nuts. Reason side. You multiply the moment arm by the weight, you get the torque. Okay. If you And let's do one more step of this. If the center of mass you got your weight, and let's say you've got a pull from here, okay, you're trying to balance this thing on this pull, right? Imagine my finger had a triangular cross section, okay? If you try to balance it here, I started to say torque to the right, the torque produced by the part of the, I'm going to say it, it's not quite right. Say torque from the right minus the torque from the left. Okay? That has to equal zero. Without totally making the connection, I'm going to say the position of the center of mass equals the torque over the total mass. Okay. Now that's pretty clearly to prove. If you assume that this meter stick has no weight, it's weightless, but it's strong enough to support this thing. Okay, so the torque I have about this end is just equal to this distance times this weight, right? I'm kind of using mass and weight interchangeably also, and there's a distinction. Weight is what gravity does to a mass. And I'm going to use mass as if it's weight because that's what your textbook does. That's all you need in order to do center mass. Rigorously, if you multiply everything in the numerator by the acceleration of gravity and everything in the denominator by the acceleration of gravity, you have torque in terms of actual torque and weight. Okay. And I'm not going to make that distinction. I'll save that for your physics class. Okay. So in this case, the torque equals this distance times your weight. And the center of mass is right here. If this meter stick is massless, this will balance right here. Okay. Now, if I got other masses, it still holds true. I don't want to go too deep. Kind of took my word for it. Think about it. If you want to talk more about it next time, you can let me know. Okay. But this is position of your center of mass is torque over total mass. Okay. To get the torque of this thing, about any point, let's just say about the left hand, we consider an increment. We divide our, say this is our x-axis here. We divide our x-axis from one end to the other into little strips. Make sure we're recording. I wish this thing would really tell me. So I can just glance at it and confirm if I'm ever. Keep stating, keep just going away. Okay, anyway. Okay, so what I could do is, as we always do, or at least as I'm trying to get in the habit of doing, is we look at one little strip. Okay, so this strip with delta x at x equals x star. Now I could say with delta x sub I at x equals x sub I star. Matter of fact, I'm going to do that. This is the ith interval. And you have an ith increment. The width is delta x sub I. That x equals x sub I star, any x sub I within this interval. Moment, I'm going to use rho, although if you're working in spherical coordinates, you're probably going to want to use a different symbol for your density. You don't want to use d because you got dx's and dy's and dz's. You got a rho for your radial coordinate. But actually, I'm going to take back what I just said. This is actually, I'm thinking in terms of something that we can do linearly. So I'm just going to say a lambda of xi star. Lambda is your density per unit of length. So then we multiply lambda of xi star by delta xi to get the mass, right? Okay, mass is lambda of xi star times delta xi star. Torque. I'll just use tau. And I'm going to use x equal x sub L for the position about which we're calculating the torque. Often that'll be the left side, but it could be any position you wish. Okay. So I'm going to say the torque sub L here, indicate that's a torque about x equals x sub L. Equals what? Delta M sub I. And this is the contribution of the torque from the ith increment. Going to be your mass times xi star minus xi. Now I'm being really sloppy, but I'm going to continue to be sloppy because this is why I think your text does it. By sloppy, I mean this calculation of torque. First of all, This is not a force, it's a mass, but remember, if I multiply it by the acceleration of gravity, it becomes a force. Secondly, if the moment arm is here and the weight is here, the torque by right-hand rule is into the board, which would be negative. It's a clockwise, and a torque is positive if it's counterclockwise. So you got to be careful of that distinction. But for this example, at least, it's not going to make any difference in formulas in the text, I think. I haven't looked closely to see whether they do. I know what they are. And I'm not sure what they do with their signs. But I think they might have the torque backwards. Maybe not. Okay. So anyhow, here's your torque. The torque is actually a vector. It's actually a cross product of the force you get here with moment. Okay. And it's worth knowing that. But right now, we'll just deal with this. Okay. So does this make sense now? X of I star minus X L is this, right? So here is Xi star minus XL. That's the moment arc for the torque. The mass is associated with a downward force here. So this product is associated with the torque. It's not actually a torque, but if you multiply it by the acceleration of gravity, it is. It's not going to matter because we're going to divide by the mass. Okay? I believe we should divide by the weight. You'd have another G in your denominator. Okay, well. So mathematics is not always totally consistent with physics. Sometimes you got to make a few allowances. On the other hand, physics is often not as rigorous as mathematics. So, mathematicians and physicists are always at each other. Since I'm doing both, I'm always contradicting myself. Okay. And contradict myself for other reasons too. Okay, so here we have it. Now, how do you get the position of the center of mass? Well, I got to make another step before I get there. So I'm going to have to maybe move up here. So your total torque is sum of all your delta M sub I times Xi star minus XL. That's kind of compressed, but it's the same expression down here. Okay. So all I've got inside of here is this expression, but I'm summing it up now over all these strips. Well, it's approximately equal to this. It approaches the limit as your delta Xi's all go to zero, and that's a little sloppy. Okay. This sum y equals 1 to n of delta mi times Xi star minus XL. And that's written small and sloppy. It's the same thing as this, same thing as this. And that is equal to the integral from 0 to the integral from 0 need to fill in just a little more information here. This is XL. This will be XR, X left, X right. Okay. It could be A and B, but it's the integral from XL to XR of I'm not having my best day here. I never did fill in what delta MI is, right? I mean, I said what it is up here, but I didn't use it in my expression. And I'm going to have a hard time using it in my expression because I don't have room. And my only recourse, I think, is to, oh, damn it. Well, give me a second. Oh, wait a minute, I've got a blackboard behind this. No idea. I have to put a blackboard behind it. I've already got it. Okay. So I'm gonna erase what I started to write here. I could easily enough write it out at this point, but take up more room than I've got. So I'm gonna write this down. On the left, the sum of I equals 1 delta m sub I times x sub I star minus x sub L. And we established here. That equals the sum of I equals 1 to n of what's delta m sub I? It's lambda of x I star times delta x I times x I star minus x sub S. Okay. Again, your mass is just density evaluated at your sample point times your width of the interval. Okay. And this is an approximation, but as your mesh of your partition goes to zero, partition, you know, what I've partitioned when I've drawn these lines is x naught, x1, x2, x3, etc., up to x sub n, right? That's what those lines represent, x coordinates from x0 to x sub n. X sub 1 is this, and your delta x sub 1 is your x sub 1 minus your x0 is this. Okay? This is your typical increment. This is called your ith increment. This would be xi minus 1. This would be xi. Okay? You're at delta xi goes from xi minus 1 to xi. So your delta xn goes from xn minus 1 to xn, which is this last one. So look back at partitioning and Riemann sums. It's everything we do is based on partitions. Okay. So what we've done is we've partitioned this interval. We've looked at the typical increment. We've got expressions for the mass, the torque, in our typical increment. So here it is. Now you multiply the masses times the moment arm, the distance of the fulcrum. Fill in how we get the masses. We multiply the density by the length of the increment. And this then approaches the integral from z from r. X sub L x sub r of lambda of x times x minus x sub L dx. That's our total torque. Total mass. We just add up our m sub i's. That approach is going to limit the interval. The one end of the partition to the other. That would be XL to XR with the notation I've used here. That's lambda of x dx. That's what we're integrating. Okay. The x coordinate of your center of mass, x coordinate of your center of mass is your torque over the total mass. Okay, I'll use M. Oh, that's a TOT. That equals the integral of lambda of x times x minus xl dx. That's from whatever your left is divided by the integral left to x right of just lambda of x dx, which you should understand is your total mass. Now there's some terminology involved here. And this is going to be important because we're also going to do moment of inertia. This is called the first moment of this. Okay, this is your mass interval. Okay, this is the first moment because why? I'm multiplying the mass by the moment arm. Okay. So here I've got the mass interval, and here I've got mass times moment arm integral, i.e. the first moment of the mass. Okay. Now, I could do all that for the whole meter stick. since the mass density of the meter stick is always the same, it's going to turn out that if I integrate the first moment divided by the integral of the mass, okay, let's just say the mass increment is 0.6 grams per centimeter. So that's my lambda, 6 grams per centimeter. I integrate that from 0 to 100 centimeters. I get the total torque if I try to support her above this end. Okay. If I integrate that 0.6 grams per centimeter from here to here, I just get the total mass. If I integrate that 6 grams per centimeter in each increment times the length of the moment arm, well, that's what I'm doing here, isn't it? Okay, that gives me the torque. Torque I need to exert here to support this meter stick around this fold of this end. Now, be careful, centrifugal force might get you. But if I want to move this thing and want to accelerate this thing up to a certain speed here, it's going to take a certain amount of energy. Okay. That energy is going to be related to the second moment. Okay. So we get this new integral, which is called the moment of inertia. And the moment of inertia actually tells me how hard it is to accelerate the thing. Okay. It's the resistance of all those mass increments from this end to that end against being accelerated. You think that would be torque, but it actually, and you know, derive with energy considerations in physics. The integral would look a whole lot like this. But I'd have to square this. Kind of related to the idea of kinetic energy is 1/2 mv squared. You got momentum is equal to mv, kinetic energy that depends on mv squared. There are higher moments. Have you had a statistics course, anybody? Here's standard deviation, the first moment. Okay. Maybe it's a second moment. It's a moment. You got this thing called kurtosis of a distribution. It's a higher moment. Okay. You got moments upon moments, just depending on the square, on the exponent here. And that's an important idea. So what you have is 0th moment, first moment, second moment. And of course, this is 0th moment because you have x minus x over the 0. That's just 1, and you have this. Make sense? Now, I hope that this was all visible when I did it. I just had a better display to look at, but okay. Right there's the whole development. Again, they call them connections, in case that wasn't visible. We've established that the torque is delta Mi times this. We established that the mass increment is this. So all we're doing is the torque is the sum of mass times moment arm. Okay, just the sum of all these. And then I've expanded that to include the actual expression for delta M sub I, which is what contains the delta X sub I, which is going to be necessary to get the interval. Okay. And then I say the limit as all your delta xi is uniformly approach zero, or as your mesh approaches zero, depending how you set it up. In the limit, as everything, as all your increments become tiny and approach zero, this sum approaches this, and that's something you should know from your first semester calculus, so review the details of that, okay? Total mass, we just add up all our n sub i's, which gives us, there's your n sub I, and that gives us the integral lambda of x dx. Position of your center of mass is just torque over total mass, which is what I said here, okay? And hopefully it makes some sense intuitively. Whether it does or not, that's what it is, and you want to think about it, think about why it is. That gives you this integral over this. Now, I explained why already. This is the first moment, this is your zeroth moment. Okay. And that much was visible, whether the entire expression was visible, I can't guarantee. Zeroth moment, first moment. Second moment. The second section, the last thing we're doing in this chapter is integrals for mass moments. Center of mass moment inertia to make calculations. And I just say that, you know, these integrals also apply in statistics. Okay. Given 15 minutes, I can explain why in pretty comprehensive terms. Some guys I will do with Discovery School groups. 15 minutes. These are high school sophomores or juniors. So it's not a difficult connection, but I didn't explain the inputs. I just explained the ideas of mainly the idea of standard deviation as a whole. Okay. Now, what do you do when you have a three-dimensional object? Because really, you know, this is the context of multivariable. All this stuff is part of first year calculus. But I don't know that anybody really remembers it. Okay. I don't know how much it was stressed, and even if it was stressed, there's a limitation to what people can understand in February of a first year calculus course. Okay. So we might have done it. We might have done it by memorizing formulas that you then forgot and didn't really understand. Okay. And if you haven't had physics, it'd be hard to understand. I'd had physics, I'd done experiments, center of mass in high school. So it made sense to me. I thought it was really neat. If you don't have that background, did gym once in middle school, didn't follow up good physics course in high school, and then, and again, I was taking the rigorous physics course. Every freshman took the physics and the calculus sequence. Every freshman at the school, unless they had advanced placements, some took advanced. There's no such thing as AP at that time, but some people would put into accelerated. If they hadn't counted this course in high school, it had good physics school. Okay. Very few high schools offer calculus. Mostly Eastern prep schools. Those guys had an advantage. I don't know if I'd have survived a calculus course. No, it does. Okay. Again, this is first year calculus. You probably ought to review it in your first year calculus. Okay, what do we do now if we have a two-dimensional object? Okay, so let's just say we've got a two-dimensional region. And we got a coordinate plane somewhere. Or set of coordinate axes. It's in a plane, so make it a coordinate plane by opposing a set of coordinate axes. And we have sigma of x, y, or sigma of r theta. Because in rectangular coordinates, the two coordinate systems that we deal with in this course are rectangular and polar coordinates. Now I'm starting to tell you what the center mass is, and I just decided, no, it's bigger than that. See the finish that integral smooth way. It's a double integral over the region. And I'm just going to write sigma dA. If the region is a rectangular region, then it's sigma of xy, dx dy, or dy dx, whichever is easy. Okay? If it's polar, then your region's described by inequalities in polar coordinates, and you have limits on that integral, and it's be a sigma of r theta times r dr d theta, or r d theta dr, whichever. Okay? We understand that, right? Familiar with that? Because that's what we've been doing, but we've only been doing it about a week. There's your total mass. Give it a symbol. I'll use a capital M for the total. Okay. I don't have room to do that here. The torque of this region about the y-axis well, let's just take a torque of a typical mass increment. Or this is an area. It might be a dx by a dy, or delta x by delta y, or it might be a delta r times r delta theta. Okay. So I'll write that up for just to remind you. That could be I said r delta theta times delta r, that's the way you do it. Remember, your r delta theta is one dimension of this approximate rectangle, and delta r is the other dimension. Okay. So your typical increment I'll call P sub I, that is an X sub I star, Y sub I star, or an R sub I star, theta sub I star, depending on whether you're in polar or rectangular coordinates. Does that make sense? Then and again, my notation here. Simplified. Fix that easily. It should be a P sub ij. And a comma. For a delta A increment, the sample point has got two coordinates. Maybe it's an X coordinate and a Y coordinate. Maybe it's an R coordinate and a theta coordinate. But your X coordinates are going to be numbered differently than your Y coordinates. So I'm going to call that XI star, YJ star, RI star, theta J star. Okay. So you would partition your X's with vertical lines. Okay. And that'd be like X0 through Xm. And you call your typical X increment X sub I. And to draw that out a bit, your Y increments could be Y0 through Y sub M. Okay, you've seen that if you've read your text, standard rotation. And they'd be numbered with J indices. They wouldn't be numbered with the same index X is. If it was always just XI star, YI star, you'd have a diagonal series of increments and nothing else. So think about that, but you gotta have different increments in these things. Okay, so the delta M total mass is sigma of P sub I, which could be sigma of Xi star, Yj star, or sigma of Ri star, theta J star, right? Pij, that is times delta A. The delta A probably has an ij on it too. Okay, so here's your typical increment delta A, but if you try to number them all, you got a number along X and you got a number along Y, right? So it's the ith X interval here and the jth Y interval. Okay. It actually gets a little more technical than that when you do the thing because your Y interval depends on your X interval. And you just don't number all your YJs. You just don't partition all the way from here to here for every X increment. You partition only from here to here. If this is your X value, or from here all the way up to here, if this is your Y value, and so forth. Okay, so I'm glossing over a little bit of that to give you the most general picture. If I show you all the trees, you're going to have a hard time seeing the forest. So I'm kind of showing you something kind of intermediate there. Okay, does this make sense? You multiply your density by your area. That's what it comes down to. And you've got area increments, they're doubly indexed because you got to know where the X interval is, where the Y interval is, and the PIJ. You're in an IJ interval, and this is a sample point. And I should call it PIJ star, since I've got stars on it. Okay. So again, remember, PIJ is either XI star, YJ star, or I star, sigma J star, depending on your coordinate system. Okay. So that's a contribution to your total mass. Now we want the contribution to the torque. So the contribution of Okay, I'm going to say this is a contribution AIJ to the torque about the y-axis. Okay. What it is it just going to be delta M IJ, which is like your force. But again, multiply gravity, my acceleration of gravity, but that. So delta M IJ multiplied by what? If I know the mass of this increment, how do I get its torque as measured about the y-axis? And now for the reasons I just stated, just so we have this photo camera, if my y-axis is this way, so I'm holding this thing, let's just say I'm holding it around the y-axis, right? If the mass increment is here, then I've got a moment arm, okay, that I multiply by the mass, right? If the mass increment is out here, then I multiply that by the moment arm. Now, what's the symbol for the moment arm? Well, this is perpendicular to the y-axis. The y-axis is here, so I'm calculating the torque about the y-axis. So the moment arm from here to here is just the x-coordinate. This is x equals 0. This is x equals 10, 20, 30, 40, 43. Okay, in this case, the moment arm is 43. It's like x minus xl, except xl is 0. Okay. It does a fairly good job of explaining it. I did have to look at the book to see what the notation is. Call this tau y, the torque about the y-axis, which is the only thing that logically could have been. It's what I wanted to write. But I wanted to make sure of the about the y-axis this times xi. Now, could be all right as a cosine of theta j. Okay. And sometimes you want to do this in polar coordinates. usually going to want to do it next y coordinates. Most of the problems you're going to see do it next y coordinates. Because you're still going to do the torques about two perpendicular axes. And in polar coordinates, the coordinate axes don't have the convenient perpendicularity they do here. Okay? You don't even have a theta axis. And you do have an R axis, but then it rotates, and, it gets confusing. So, does this make sense? Xi is your moment arm for this thing, the IJ. So your total torque, skipping just a couple of steps that are pretty obvious from what we've already done. Step like left out there. Okay, your delta MIJs become DMs, but DM is whereas it attribution of the torque is this, right? So it's just X times your density. That's the first moment. Integrated over the whole thing. She's the first moment of this whole thing about the y-axis. Okay. In this picture, some of the x's are negative. So then the x's here will be negative. Because it gives you a torque that's in the opposite direction, the torque you get if x is positive. So if this increment is on the left, your x is going to be negative. Your torque is going to be negative, even though it's really positive. Don't worry about that. Okay. Just worry about the fact that the integral works, whether this thing is on both sides of the y-axis or just one side. So the x coordinate of your center of mass is, I got tau total, this is tau y, and I won't even bother writing total here because we're doing the integral, we know it's the total. Tau y over m. By analogy, y coordinate of your center of mass tau x over L. And all we do to get this is, okay, now we're going to rotate about the x-axis. So we're going to consider the torque of this increment about the x-axis. And then we're just going to sum up those torques to get an integral, which is going to be the integral of y sigma dA. Now I'm going to write out bigger expressions. This is what you need to understand. Okay, And if you got something in 3 dimensions, well, then you could have a torque about the z-axis also. It's a little weird because, you know, it's a little hard to think about gravity there, but the form of the integral comes out in a very straightforward manner. So what we can say now, and I do want to double check, make sure I'm giving you notation of the text. What talk about the y-axis is the integral over the region of y times sigma dA. This is your moment arm. And I said it wrong, it's x. This is moment arm about the y-axis. This is your okay. Moment arm times mass is your torque. It's tau sub y because it's torque about the y-axis. Torque about the x-axis. Sigma dA is still your moment arm about the, well, sigma dA, I'm sorry, still your mass increment. Y is your moment arm. The x-axis. Okay. I sub x is your moment of inertia. About the x-axis. What do you think the moment of inertia would be about the x-axis? Well, what's the difference between torque and moment of inertia? It's the first moment versus the second moment. Okay. The first moment, you have just your moment arm. The second moment, you're squaring your moment arm. Now, we're not using an x minus xl or a y minus yl or anything like that because we're using xl equals 0 or yl equals 0. We're integrating about the x-axis or the y-axis. So just to wrap up, the moment of inertia about the x-axis is your double integral over the region. X squared sigma dA. I'm sorry, that's y squared sigma dA. And moment of inertia about the y-axis is the integral over your region of x squared sigma dA. Where sigma is expressed whatever coordinate system, usually for these in rectangular coordinates. Okay. If you're in polar coordinates, then you're going to replace your x by r cosine theta and your y by r sine theta. Now that's an overview. You have to work through the details. I don't have the problem sets up yet, but I'll get them this afternoon. So have a good weekend. This stuff's a little challenging, but the whole idea of first moment and second moment, which extends into third and fourth and fifth moments, is kind of important in a lot of ways. So this is well worth digesting.